Look at the atomic structure of solid steel. The crystalline lattice is perfectly ordered, incredibly dense, and bound by forces that can support tens of thousands of pounds per square inch without yielding. But look at a catastrophe like this collapsed truss bridge. The heavy steel beams in this span didn't snap. They didn't shatter under an overwhelming vertical weight. The material itself was strong enough. Instead, they fell victim to a phenomenon called buckling. When placed under heavy compression, the structural member suddenly and violently folds sideways, dropping its load in an instant. Buckling is a failure of geometry. It's an instability caused by the shape of the object, completely bypassing the actual strength of the metal itself. If you take a short, thick block of steel and push down on it, it behaves exactly how you'd expect. It acts as a stump. It will resist the pressure until the weight becomes so extreme that the metal literally crushes. As you stretch that shape upward, you change its slenderness ratio, which is the length of the object divided by its radius of gyration, or thickness. Once that ratio crosses a threshold of 10, the object stops being a stump and mathematically becomes a column. You can see this physics problem in action with Charlie Chaplin's famous cane. He applies a direct, downward compressive force by leaning on it, but because the cane is slender, that downward energy is redirected sideways. The cane bows outward laterally. A column's vulnerability to this sudden outward bowing is dictated entirely by that ratio. The taller and thinner it gets, the more it wants to step sideways. Structural engineers classify these vertical supports into 3 destinies, based entirely on their shape. The first is the short column, which has a very low slenderness ratio. Inside a short column, the physics are straightforward. The compressive force flows in a pure, uniform line straight down through the material. It exists in a state of stable equilibrium. If you push on it, it stubbornly resists any change in its shape, right up until the applied load exceeds the absolute limit of the steel or concrete and the material begins to crush. A short column fails in a highly predictable battle of raw material strength versus the weight stacked on top of it. The second destiny belongs to the long column, defined by a very high slenderness ratio. Here, the rules of brute force no longer apply. This diagram shows the exact tipping point for a long column, a mathematical limit known as Euler's critical load, or PCR. This line represents the precise moment geometric stability is lost. As long as the applied weight stays below PCR, the long column remains in stable equilibrium. You can shove it from the side and it will vibrate briefly before safely returning to a perfectly straight vertical line. When the weight perfectly matches Euler's critical load, the physics shift. The column enters neutral equilibrium. It bows slightly under the pressure and holds that ghost-like curved shape, balancing on a razor's edge without failing. Add even a microscopic fraction of an ounce beyond PCR, and the column falls into unstable equilibrium. It instantly leaps outward into a deep, extreme lateral buckle. Long columns experience a catastrophic geometric death the millisecond they cross Euler's invisible threshold. The steel never even comes close to reaching its crushing point. The third destiny is the intermediate column. These supports live in an unpredictable middle ground. They aren't short enough to simply crush, but they aren't slender enough to cleanly bow out. This chart shows how engineers map this territory. The Euler buckling curve is modified by Johnson's parabola, curving downward to create this shaded area, a highly specific danger zone where the formulas overlap. Inside this zone, the column suffers a dual failure. The internal material begins to yield and crush under the compressive weight, while simultaneously the shape of the column begins to buckle sideways. Because of this combined attack, intermediate columns present a uniquely difficult challenge. Engineers must calculate to protect the structure against 2 distinct laws of physics at the exact same time. Scale this physics problem out, and you see the hidden skeleton of modern construction. Every time a skyscraper rises above a city, it relies on thousands of vertical steel pathways. Every single one of those supports is a calculated risk. Whether it's holding up an observation deck or a parking garage, its survival depends entirely on its slenderness ratio. Structural engineers calculate geometry to outsmart Euler's critical load, accounting for the raw weight of every beam and the specific shape of the entire frame. The safety of our entire built environment hinges on keeping those columns mathematically separated from their geometric tipping points. The column's height and thickness are governed by a second physical factor, the massive bolts anchoring the support to the ground. Whether the joints are pinned to pivot freely or fixed rigidly in concrete determines the column's effective length, dictating precisely when and how it will buckle. Manipulating those end connections becomes the engineer's final, most powerful weapon against the invisible threat of buckling.